So I'm Antonio Torralba. Welcome to the Deep Learning Day. It's going to be a little bit more than just deep learning. And so we will start with an introduction, and Philip will kind of set the stage and tell you what the day today will consist of. And I hope that you enjoy.
Okay. Yeah, thanks for coming. So just kind of get a show of hands of who has taken a deep learning class, studied deep learning, programmed deep nets. Okay, and who has never touched a deep net, doesn't know what a deep net is at all? Okay, good. So I thought we would have a mix, and we're going to try to make this accessible to everyone, but also include some of the latest technical content. Okay, but that helps. So many of you have seen this. I'm sure all of you have heard of, deep learning. This is one of the big technologies driving AI these days. Okay, so in this first 15 minutes, I'm going to kind of give you the schedule for the day, but also give you a few of the basic building blocks of what a deep net looks like that we'll then see elaborated in the remaining lectures. Okay, so here's the schedule, and it follows kind of the timeline of deep learning from 1986, which was when the backpropagation algorithm was published, which was one of the kind of first moments in getting an algorithm to be able to train a neural net to do something interesting, up until today. And the first 15 minutes is going to be deep learning, and then the rest of the day will be everything that you kind of build on top of that, which you could call deep learning. It's associated with deep learning, but it really goes beyond the 1980s version of deep learning. Okay, so I will give you the basic idea of training a neural network to fit data, and then Kai Ming will come in for the next lecture on the next part of this tech stack. We're going to build up this tech stack, which is the stack that powers modern systems like ChatGPT. So the next piece that you really need to understand is generative modeling. This is the main way that we train our deep nets these days, is with what are called generative modeling objectives. And then on top of that, we don't just do any old type of model on any old type of data. For the really powerful systems that you're seeing today, they're mostly large language models. So we'll have Yoon talk about that. Of course, there are other ideas too, but this is the tech stack that we're going to tell you about today, which is for the kind of modern, really powerful popular systems like language models like ChatGPT. Okay, so then generative modeling really got to be a big topic in deep learning in the 2010s. I put down 2014 because that's when two landmark papers were published, VAEs and GANs. But it's fuzzy. These years could be shifted around a little bit. And large language models started becoming popular around 2020. That was when GPT-3 was published, and we're now currently in the large language model era of things like ChatGPT. Okay, but things have progressed beyond that. That's not the latest thing. So the even more recent thing, which started maybe around 2022, is the idea of not just directly sampling from the language model to write random stories, but doing what's called reasoning. So I'll talk about that in the afternoon. And reasoning models are what are starting to make headlines today. So for example, if you heard about DeepSeek R1, this is a reasoning model. So I'll tell you what that means. Okay, and then the very last piece on top of this stack, which Antonio will talk about, he'll actually talk before me because we switched the schedule around, but it's agents, making systems that do reasoning on top of language models that are built out of generative models that fundamentally rest on deep neural nets, but making actual agentic AI systems out of that. And Antonio will talk about that. And that's becoming a thing around 2023. Now, of course, all these ideas have their roots in much earlier work, but this is kind of the slope that I've seen. And the interesting thing, if you look at the years, I've drawn them in kind of logarithmic scale. So why are we, all trying to clamor to learn this? Because this is the real curve. This is the real timeline, okay? It's just exponential. Okay, so much is going on right now, and it's just a really exciting time. You can see that we're going pretty far beyond kind of traditional deep learning in this course. Some people choose to define deep learning as just the blue part, which I'll spend the first short talk on. But the whole stack at places like OpenAI, DeepSeek, Google, et cetera, is this current stack. Okay. Okay, so here are the times. I believe there's some printouts of the schedule in the back, or you might be able to find it online. So we'll have generative models, large language models, then we'll have a lunch break, then we'll do agents and reasoning, and then we'll have a Q&A session at the end when we can take your questions. Okay. So let me now tell you the basic building blocks, which many of you have seen before, but just so that we get on the same page to start off. So what is a deep net? A deep net is roughly inspired by how the neural nets in our brain work, right? The name is the same, it's a neural net. And in our brains, neuroscientists have a pretty good understanding of the kind of pipeline from raw sensory inputs, data coming into the eye, into the ears, being processed by different layers of the brain until at the kind of back, at the top layer of the brain, which is actually in the front of your brain, you end up having recognition and decision making and more like high level intelligence. So this is the visual hierarchy in the brain. You start with photons, you have edge detectors, which get like added up into conjunctions of edges and detected as patterns and spirals and triangles. And eventually in an area more frontal in the brain, the IT cortex, you get the recognition of cats and dogs and foxes and so forth. Okay, so what does that look like when you make a machine do it? It looks very similar. It's going to be a hierarchy of going from the raw data to a good representation from which you can make a decision or a classification. So we start with the raw data. We might detect things about that data. We then will process these subcomponents into higher order structures like segments and parts, and then we'll eventually classify, well, given that I see a blob of gray over a background of dark, and there's a circle in the, with that like a dot in the middle that might be an eye, then I'll recognize as a heron. Okay, so this hierarchical kind of pipeline that you might have coded by hand 20 years ago, now we simply replace all those boxes with kind of empty, learnable, parameterized functions, and we learn the mapping to go from the input to the output, but it's still this hierarchical computational flow. Okay. So in modern neural nets, we don't use exactly the same hierarchy that vision scientists might have come up with in the past. We have something a little more generic. We just have these layers, very simple functions that transform the data layer by layer, one by one. And a deep net is just a lot of those. Okay, so neural nets, deep nets, same thing. Okay, so the key thing is I'm going to have functions that are parameterized by weights and biases. I'll tell you what those are that map the input data to an output representation of the data, like the label heron. Okay, so here's how the whole system looks when you're going to train it. So to train this network to recognize images, you simply provide it an image of a heron. You provide it the label of what the target you want the network to output at the end. The target representation is going to be the label heron. And you provide it with what's called a loss function, which will penalize the difference between the output of the network and the target that you wanted it to output. So this is called supervised learning. And if you haven't seen these equations, don't worry. If you have, they're to remind you of the basic math here. We're going to try to find the parameters, which are going to be the weights and biases. These are like knobs. I'm going to fiddle with these knobs to change the transformation so that it will achieve what I want. It'll achieve a low loss. Low loss means low error. It's going to achieve what I want. Okay, so when I see the heron, it will output heron. And if it doesn't, I'll get a loss, and I'll update the parameters. Okay, if I see a guitar fish, this is a training process. I'll show it more and more images. Next, I'll show it a guitar fish, and I'll say, what did you think this is? Well, it'll say, I think it's a clownfish. And I'll say, well, that was a little bit off. I'll have an error, and I'll try to update the parameters, tune the knobs in order to minimize that error. And then I showed a car, and I showed 1 million images. And once I've done that, it will be able to see a new image and recognize what it is. Okay, and the way that it does that is the basic training algorithm is gradient descent. So that simply means take that objective of minimizing the loss and try to tune the parameters, fiddle with the knobs in the direction that will reduce the loss locally. And that's based on the gradient of the loss with respect to the parameters. Okay, so that looks like this. I have some setting of the parameters that incurs high loss that doesn't recognize the guitar fish and the car and so forth. And I simply set it up as an optimization problem where I'm trying to make that loss go down via gradient descent. I'm just going to walk down the slope to lower and lower amounts of error until I get a good solution to the problem. Okay. So this is just to kind of lay out the basic ideas. We'll go into a lot more interesting details soon. Okay, so the way I like to think about the elementary operations, so you can think about a neural network now as just a parameterized function that is fit to data to minimize the errors you make on predicting properties of the data. That's one level of understanding it. The next level is, well, internally, what are the transformations of this parameterized function that are achieving that interesting mapping? And the way I like to think of it is that layer by layer, you're changing how you represent the data. You're transforming the data. So you start with the raw data, and you do something to it to make it into a better format. And you do this over and over again until at the end, you get your decision. OK, so this is going to be a kind of mathematical, like little abstract picture of what's going on inside a neural net. But I think it helps us understand it. So let's just look at a neural net that's trained to classify the red points apart from the blue points. OK, so you might have done some basic linear classifiers in math classes in the past. Well, this is a little tricky because it's not actually linearly separable. You can't separate that red set of points from the blue set of points with a line. So you need a nonlinear classifier. Luckily, deep nets can do that. So this is showing the data represented as a scatter plot. So each data point is a two-dimensional vector. It's two attributes, and you can draw that in a two-dimensional plane on the left. And the whole goal of a classifier is simply to find a way of moving the red points all to the output representation of a cat, which we'll call the label 1. So the label 1 will be represented as y equals 1 and x equals 0. So y is like catness, and x is dogness. And so I want all the red points to move to the point 1, 0. That I'll interpret as the label of the data being a cat. And all the blue points should move to the label 0, 1. It should be not at all a cat, 100% a dog. So a classifier's output, which is it cat or dog, can be represented as this kind of two-dimensional picture of its belief to the degree that it's a cat, the y-axis, or it's a dog, the x-axis. OK, so all a deep net is doing is finding a way of moving those data points around. And the interesting thing is that the way it moves them around is very, very simple. Each layer of that neural network is just going to make a very simple modification to where the data points live. And eventually, at the very top, they'll all live at the right point. All the red points will have moved to the cat label, and all the blue points will have moved to the dog label. So what does that look like? There's two basic layer types. And then there's a lot of other additional fancy ones. But the two basic ones that are really the workhorse of deep learning are called the linear layer and the pointwise nonlinearity. So the linear layer is one of those transformations. OK, it's going to be a linear transformation of the data here, a geometric linear transformation. So what does that look like? So in math, it looks like this. I take my input data, which is just some image or some raw data I'm processing, x in. I multiply that by matrix W. That's a linear transformation. We call the matrix W the weights of the neural network. I add a bias, so it's an affine transformation. And I get an output which has moved the data points to a new location, x out. So people in neural net land often like to draw these as networks of neurons, but this is just a representation of that equation. I have a vector xn of numbers. I have a linear transformation, which is like every output is a linear combination of all of the input numbers. OK, that's just a matrix, a linear combination. And then I have a bias, which I can add a kind of constant to each of the output dimensions. OK, so this is two different ways of looking at the network. My favorite way is actually this. So here is a picture of that plane that represents the input data, x in. And how does that data get transformed to become x out? So a linear transformation looks like that. It's actually an affine transformation. It's a geometric transformation of that input data distribution. If the data lives on a grid, then it will make this picture here. If the data is like a cloud of red points, and I have some particular linear transformation, it will look like this. It can rotate, and it can shift and translate and scale the distribution of the data. So it'll move that data around. That data is the representation of the neural net's representation of the data it's processing on layer 2. OK, so that's the first function that it uses to move all the red points to one dot. OK, the second function it uses is called the ReLU. This is just going to be for each dimension, each neuron I'll take its value, and if it's below 0, I'll set it to 0, and it's above 0, I won't do anything. OK, so it's like a clipping type of function, clips off the negative values. And here's what it looks like in terms of how it transforms data. All the data in the negative part of that plane, in negative x or negative y, gets clamped to the axes, x equals 0 or y equals 0. And the data in the positive part is an identity. Nothing changes there. It doesn't do anything. Okay, and so if I apply that to a cloud of red points, then this will be the effect. The ReLU tries to kind of push everything onto the axes of this high-dimensional space, this neural net representation space. Okay. So those are two very simple ways of moving around the points, and there's a bunch of other ones. I'm not going to talk about all of these, but we have the linear, the ReLU, we have normalization layers, which kind of push everything onto a sphere, and we have softmax layers, which kind of are another type of normalization effectively. Okay, so simple geometric transformations that take your raw data distribution and move it around until you have achieved an arrangement of the data. You've moved the blue points apart from the red points. So I'm only showing the red points here, but what if we look at the blue points too? So here is a 5-layer neural network. This is being trained with gradient descent, and I'm going to show you a movie of how gradient descent will update the transformations to move the red points apart from the blue points. So the top of the network, we're going to want the blue points to all live on x equals 1, y equals 0, and the red points to all live at x equals 0, y equals 1. That's labeled for cat and dog, okay, or two classes abstractly. The input, the representations are all entangled. You can't separate them. And then layer by layer, we're going to achieve this transformation. Okay, at initialization, it's basically not doing anything interesting. It's just kind of smushing all the red and the blue points on top of each other, and it looks like all blue, but that's just a rendering artifact at the top. Okay, so here's what it looks like. So this is not hiding anything. This is really this is a neural network where every layer is a two-dimensional transformation. Usually they're high-dimensional transformations. This is just a two-dimensional transformation. And first, the linear transformation at the bottom, the first linear layer kind of stretches everything out. Then the ReLU snaps everything onto the two axes. And then another linear transformation kind of stretches it in a different direction. And it's trying to kind of stretch and pull things such that somehow we're going to get the red points apart from the blue points. And you might be thinking, this seems really impoverished. Like, how could it possibly disentangle complicated data distributions where the classes are all overlapping in different parts of the space? And the interesting thing is, yes, a neural network with only two-dimensional, 2 neurons per layer, two-dimensional transformations is not capable of doing everything. It works in this case, but interestingly, a neural network in high dimensions, just using these linear and pointwise nonlinear transformations, can fit any function. It's called the universal approximation property. It can fit any continuous function. Okay, so at the top of the network, we now have all the blue points shifted to one cluster where x equals 0, meaning full belief it's a dog, and all the red points to y equals 1, which means 100% belief it's a cat. Okay, so I'll show you that one more time. This is what it looks like to train a network. Okay, so this is the way I like to think about neural nets and the fundamental building blocks, geometric transformations of a data distribution that go from raw entangled data to better organized data from which you can make a decision, a prediction, or potentially just like generate pixels, which Kai-Ming will talk about. Okay, so I think that was the whirlwind tour of just getting you to think about neural networks. Let me take 1 or 2 questions, and then Kai-Ming will come on. Yeah. Yes, ReLU is rectified nonlinearity, or rectified linear unit is the acronym. So linear and a very broad class of pointwise nonlinearities have the property that they have universal approximation property. You can fit any function with those if you stack enough of them and you have enough neurons per layer. But it's not anything. It's not absolutely anything. Yeah, you can have some functions that are not universal. Yeah. Okay. Any more questions? And then I think we'll do Kai-Ming. Yeah, one more.
Question. The whole goal is the outside object represents where you're trying to go. The cat,
yes.
The dog. So like, what they try to align be all the different cat faces, and this line is all the dog faces. Is that the way? Is in this it was just a single point, but then you're trying to get it to the edges. What does the whole edge represent?
So the whole edge actually represents, in this case, technically the belief, the probability that you think the image is a dog. So it's not saying like what type of dog or all the different types of faces. It's just if the point had landed like here, I would be saying I have 50% belief it's a dog. I don't know if it's a cat or a dog. So really what I'm showing you is called a simplex, but I didn't get into the full details here.
Like up and down.
Yeah, up and down is like my belief of cat, and left and right is my belief of dog. That's the goal. Yeah, so that's what I'm showing you as the goal. Yeah. There is a point, yeah. Yeah.
That's why, yeah, it's like, because you're not just trying to push them to a point, you're trying to push them to the edge. So trying to figure out why you're saying push to the edge.
Yeah.
Trying to push to a point. What
So
does that whole edge mean?
this whole, it's actually, this line is going from my belief that it's a cat to my belief it's a dog. And intermediate points mean I don't know. It means 50-50. And I want all the red points to be, I'm sure it's a cat, and all the blue points to be, I'm sure it's a dog. But during training, it's not sure. So it's going to try to gradually become more sure and pull them apart. Yeah, that's the idea. Okay. One more, and then we'll go, yeah. Oh, yeah, go ahead.
Can you go back a little to the graphs of the, yeah, right there. How do
Yeah.
you read those wiring graphs?
The wiring graphs are just showing, like, this is a vector of inputs, xn, so it has indices I. And this is a vector of outputs, and the dependencies, like the jth index, or the ith index of x out is a function of the ith index of xn plus this global kind of potential here, and that's what that layer is doing. So it's kind of showing the dependency structure. Okay, I think we should move on to Kai Ming, and I'll be back in the afternoon for more.
Thank you.